As a budding developer, at some point, you'll move beyond basic programming and start designing systems which are meant for production. Production systems have to be robust, maintainable, and designed for scale. This means that you need to incorporate best practices and good design principles in your code. And here is where you can learn from programmers who have trod the same path before you. The same situations have come up over and over again, and programmers over the years have developed design patterns in order to deal with these situations. So, what exactly is a pattern? A pattern is anything that expresses structure in your code. A pattern can be thought of as an elegant solution to a complex and difficult problem. This is a problem that many developers have encountered, and they have found structural solutions for these problems. A pattern is not something that is one off or for a very specific and narrow use case. It's for a general problem that has been encountered in many situations. The fact that a pattern is a solution that fits many problems means that a pattern should be easily reusable. This is an existing solution that can be adapted to fit a current situation. Patterns are typically out of the box solutions that are flexible enough so that they can be modified and adopted to many different situations. Patterns reflect the experience of developers who've encountered these situations before us. Another characteristic of a design pattern is the fact that patterns are proven solutions. Patterns are an approach to software development that have withstood the test of time and have proven themselves in many situations in many contexts. They have been developed over years based on common problems that developers have encountered. Patterns are solid, well tested, and robust approaches that reflect the experience and insights that developers that help define these patterns bring to these patterns. Now that you have a big picture understanding of what a design pattern is, let's express it in a single sentence: repeatable solutions to commonly occurring problems in software design. A pattern cannot be called a pattern unless it's a solution for many common use cases. It has to be a repeatable solution and to commonly occurring problems. If you set up some structure in your code which has a very narrow application that is very specific to your use case, well, that's not really a design pattern. It's quite typical for design patterns to solve commonly occurring problems. Patterns are generalized solutions that doesn't require that they be tied to a specific problem. Why would you choose to apply design patterns and incorporate them in your code? Well, identifying a problem that you might encounter while setting up your infrastructure and using a design pattern to provide a robust solution can improve the speed of development as well as the quality of design of your code. Once you've studied a breadth of design patterns and have seen in what context and in what situations they can be applied, you'll be able to identify the situations in your code where a design pattern is needed. The patterns that we'll encounter in this learning path have not been lightly designated as design patterns. They're based on clear, well established principles that have stood the test of time. The patterns that we'll study have proven themselves in multiple situations over the years. Patterns are not meant to be an exact solution. You can't use them directly. You'll have to tweak them based on the principles that they embody. And applying these patterns can help developers head off minor issues that can be major problems down the line in the application development process. Using patterns force us to code in a more organized and structured manner, making us think about problems before they arise. When you think of any design pattern, let's say the observer pattern, you'll find that it has many use cases. Observers can be used to send out product notifications. They're used in event handling in JavaScript. They're also used to set up publishers and subscribers. These generalized solutions are not tied to a specific problem or to a specific domain. Patterns also need not be tied to a specific programming language. The implementation of a pattern in different programming languages might be different, but the objective and the general structure remain largely the same. And here is one of the most important points that I've mentioned earlier. They are not an exact solution to a problem. You can't just take a pattern and apply it blindly. You have to study your specific use case, understand what tweaks and modifications are needed, and use the pattern as the general structure of a solution that you're going to apply. So, how do we know what exactly a pattern looks like? How do we identify a pattern? If you were to take a walk in the wild and you were to run across several different principles and solutions, how do you know which of these can be rightfully considered a design pattern? While defining a design or a structure as a pattern, we can look for a few identifying characteristics. The first of these is that a pattern provides an actual solution rather than just specifying principles or best practices for your code. A pattern is a solution that you can adapt and reuse, not just principles that you have to follow and keep in mind. Let's take a look at a couple of examples here. Maybe this is the question that you're wrestling with while you're developing your application's code. How do I allow enumeration or iteration over the elements of a collection? What methods do I need to expose? What pitfalls do I need to watch out for? Well, you don't need to think very much. All you need to do is take a look at the iterator pattern that is meant specifically for this purpose. The hallmark of the iterator pattern is that you can access the sequence of elements in a collection or any aggregate without any knowledge of how the underlying collection is represented. Maybe the question that you're wrestling with is slightly different. How do we ensure that the APIs exposed to users are simple and abstract away the complexities of the system? In the real world, systems are made up of many moving parts that interact and communicate with one another, and these systems can get arbitrarily complex. You want your clients to use an intuitive and simple API and abstract away the complexity? Well, there is a design pattern meant exactly for this, the facade pattern, which constructs a simple facade over a complex subsystem. Another important characteristic of a design pattern is that the solution that it specifies should be thoughtful, elegant, scalable, applicable in many situations. It should not be an obvious solution which is a result of just first order thinking. Now, you might say, though, that there are many design patterns that I find obvious. Well, that's because of their ubiquity. As patterns become more common in software design and in frameworks, the more popular patterns may seem obvious, such as the observer pattern. Event handling systems, they are observers. The observer pattern is a pattern which seems obvious in retrospect. Here is a problem that you might be wrestling with as you write your code. How can you ensure that all operations of a certain kind are performed using the same object? Let's say you're performing operations on a database and you want just a single connection to exist between the database and your application code, and you want all operations to be gated through the single connection. Well, this is a classic example of the singleton pattern. A single global object, exactly one instance of this object, exists in our application code. Another common problem that you might encounter when working with a real code base is dealing with legacy code. A possible question that you might then ask yourself is, how do I get clients to work with both legacy APIs and new APIs without burdening them with the differences that exist between these two APIs? Well, that's exactly why we have the adapter pattern. The adapter pattern adapts legacy components so that legacy components and newly developed components both expose a uniform API to clients. A newly defined or developed pattern may not be called a design pattern till the solution has been proven at scale over many years of experience and in real world code. Here is an example of a situation which is so common so as to be ubiquitous. How do you wire up multiple event listeners to UI widgets? That's where you use the observer pattern. Here is another example. How do I implement undo in my application? Once again, a common problem with a standard solution. You use the command pattern. In this learning path, we'll focus primarily on design patterns and not design principles. We'll, of course, be discussing all of the different types of design patterns in a lot of detail, but in just a bit. It's important that you have a good understanding of the principles of good design so that these become ingrained and a part of your development process, whether you're implementing design patterns or writing other kinds of code. We've already discussed this fact in a lot of detail. Patterns provide elegant, reusable solutions. They're not just principles for how you develop code and how you structure code. Whatever design pattern you choose to implement, when you write your code, you should make sure that you incorporate good design principles. Good design principles are an integral part of any design, whether it's of a pattern or some other code structure. Here are some design principles that you can keep in mind as you write code. The principle of single responsibility. A class or an object should be responsible for exactly one thing and do that well. We then have the open closed principle. A class or an object should be open for extension but closed for modification. We then have Liskov's substitution principle. If you have an inheritance hierarchy of classes or objects, derived class types should implement the same interface as base class types. The next principle to consider is the interface segregation principle. Your interfaces should be small, granular, and well defined and applicable for a single use case. Your interfaces should not be bloated and try to achieve too much. And finally, we have the dependency inversion principle. This principle states that high level modules should not depend on low level modules. Both should depend on abstractions, that is, interfaces. A slight addition to the same dependency inversion principle is that abstractions should not depend on details, details should depend on abstractions. If you look at all of these 5 principles together, you can see that their first letters make up the acronym SOLID. These are known as the solid principles of good design. These solid principles are generally applicable to object-oriented programming languages such as Java, which have classes and an inheritance hierarchy that we set up using these classes. Now, JavaScript is not really a class-based language. It's actually a functional programming language where functions are essentially objects. If you think of objects when you think of classes and work with these solid design principles, you'll construct objects that are well formed in JavaScript. The solid principles lay the foundation of good design. So let's discuss each of these in more detail. The single responsibility principle states that a class ought to have one and only one responsibility. Now, you need not apply the single responsibility principle just to classes. The same principle applies to functions and other objects as well. The idea behind this principle is that any component should have responsibility over just a single part of the functionality provided by the software as a whole. And all the services provided by this component should be aligned with that responsibility. The next principle of good design is the open closed principle. This principle states that any class or component should be open for extension but closed for modification. This basically means that an entity should allow its behavior to be extended without you having to modify the source code. If you have a component that provides the basic characteristics that you need, but you need to adapt it or change it just a little bit, you should be able to do so without modifying the code for that entity, but by extension. Now, there are several ways in which you can choose to extend the functionality of a component. The first of these, that is the most common in object-oriented programming, is inheritance. When you set up an inheritance hierarchy of your components, you have base classes which provide the interface and common functionality or characteristics of a component. If you wish to model and add in additional functionality, you can create derived classes and tweak only the behavior that you need to change. So you structure your code into abstract base classes. Others can find new ways to use that same code via inheritance. And the template design pattern actually allows for modifying code via inheritance. It's also possible to extend already existing code via delegation. Delegation is when you fire events when important occurrences take place within your code. These events expose properties from within an object and other bits of code within your software which are interested in these events can listen in and be notified of changes. This way of extending code without modification using delegation is what is followed by the observer pattern as well as the chain of responsibility pattern. And finally, another way to open up your existing code for extension is to use the composition pattern. Composition is where you use existing components, bring them together, and build more complex components. Another way to implement composition is you have a function or a class and you take in parameters or member variables to determine the behavior of this function or class. This is extension via composition. And an example of this in design patterns is the strategy pattern. Moving on to L in the SOLID acronym brings us to Liskov's substitution principle. This principle of good design states that derived types must be completely substitutable for their base types. This idea of substitution allows for the decoupling of modules. You're only dependent on the interface of the base class and the derived class, and the actual implementation is hidden behind that interface. If you can swap out one implementation for another without changing how your system interacts, well, you've implemented Liskov's substitution principle. This principle also has its basis in object oriented programming. Objects of a derived class should exhibit the same behavior as objects of the base class, and this principle constrains what a derived class ought to do. A derived class should not try and add new functionality. Instead, the derived class can change the how of the object. The derived class can change how a certain operation is carried out, but should ideally not change the what of the base class. The behavior should be similar across base and derived classes. Let's move on to the next principle of good design, the interface segregation principle. This principle states that interfaces should be granular and well defined. A single interface should not expose too much functionality or try and do too much. This granularity of interfaces means that you should choose to have many client specific interfaces instead of one general purpose interface. This interface segregation principle is extremely important because a best practice that you need to follow while coding is that you program to an interface and not an implementation. When you integrate with an API, the API forms the contract between your code and the code that lies behind the API. Don't depend on knowledge that you have on how the API is actually implemented. Just focus on the contract because that won't change. The implementation might. And this leads directly to another best practice: depend on abstractions, not on concrete implementations. The abstraction is the interface, the concrete implementation is what lies behind that interface. When you apply the interface segregation principle, you're effectively acknowledging that the interface is the contract that binds the class to implement certain behaviors, that binds a system or a component to implement these behaviors. Programming to an abstraction that is your interface is important. This principle improves the quality of your interfaces by dictating that interfaces ought to be modular and cohesive and be focused on providing narrow functionality. They should not be general purpose. Unwieldy catch all interfaces that mix many different behaviors are not good practice. The D in the SOLID acronym for Principles of Good Design stands for the Dependency Inversion Principle. This states that clients should only depend on interfaces and not on implementations. And this is important because the Dependency Inversion Principle talks of the relationship between high and low level objects. The Dependency Inversion Principle states that high level objects should not depend on low level objects. However, both should depend on abstractions. Let's say the application that you're looking to build is a text editor of some sort. Now, a text editor is made up of documents, and every document can have multiple pages. So, a document is a high level object and a page is a low level object. Document and page would both be interfaces which are implemented by concrete classes. Implementations should not reference other implementations directly. Implementations should only work with the interfaces exposed by other objects in the system. And the dependency inversion principle specifically states that higher level objects, such as the document object, should not reference lower level objects, such as pages. Pages can reference documents. This completes our discussion of the solid principles of good design. But there are two more design principles which I believe deserve special mention. The first is the principle of least knowledge. Only talk to friends, not to friends of friends. Code within a module should know as little as possible about other modules that it integrates and interacts with. So, a code in a module should not depend on the internal details of other modules that are its friends. Another principle of good design that's worth mentioning here is the Hollywood principle. And the Hollywood principle is actually closely related to the dependency inversion principle that we spoke of earlier. The Hollywood principle says, don't call us, we'll call you. This is what a high level module will tell a low level module. High level modules here will call or notify lower level modules without knowing about their actual details. They'll only deal with lower level modules using abstractions as specified in the dependency inversion principle. Lower level modules can plug in and listen on events from higher level modules. Event based messaging is often used to implement the Hollywood principle. If you go back to our example of the text editor where we have documents and pages, the document notifies the page of changes when they occur via events or messages. The document should not reference pages directly. The document should just fire events to notify interested parties of state changes, and pages which are interested in the document should just listen in on those events. This fundamental idea of high level components calling lower level components using abstractions and triggering events is ubiquitous in frameworks. So far, when we've spoken of design patterns and design principles, we've focused our attention on what you should do when you're developing your application's code. But here in this video, we'll talk of anti patterns. Anti patterns are basically what not to do when you're writing code. If design patterns give you the right way to structure your code to avoid problems in the future, anti patterns are problems that exist in your code which you should be able to identify. Anti-patterns are essentially a common response to a recurring problem that is usually ineffective and risks being counterproductive. When you code in a rather ad hoc manner without giving thought to structure or the design of your code, what usually results is an anti-pattern, an example of what not to do. Just like design patterns are robust, reusable solutions to problems, anti patterns tell software developers what not to do, what solutions have been failures in the past, what solutions can cause problems down the line. Anti patterns are shortcuts that seasoned developers use to define or describe a bad solution to a problem that resulted in a poor outcome based on their experience. Now, if you're focused on good design and on well structured code, why are anti patterns important? Just like it's important to know what to do, it's also important to know what not to do and identify situations where the solution that you have is a poor one. Anti patterns help developers describe how to get out of the bad solution and move towards a good solution. And the first step here is to describe and define the bad solution. If you have a catchy vocabulary and a pithy way to describe a problem, it's likely that you'll remember such a problem exists and be able to identify it in your code. Anti patterns offer a specific vocabulary to recognize recurring problems and offer a plan for productive solutions. Anti patterns are not just limited to software design and programming, though that's what we'll focus on in this video. Anti patterns apply to organizational behavior, project management, anything in the real world. We'll start our discussion of common anti patterns here with the software design anti patterns. And the first of these is called a big ball of mud. You'll find that anti patterns often have a very interesting vocabulary. Big ball of mud refers to a system with no recognizable structure, a system with many components, all of which interact in a haphazard manner, and there is no clear way to define how information flows. That is a big ball of mud. Now, this is often very common in the real world because of business pressures, developer turnover, and code entropy. It really can't be avoided in some cases. The important thing is to catch it early and fix it if you can. Another software design anti pattern is gold plating. This is when Your team continues to work on a product or a feature where the extra effort that your team has put in does not really add value. You're working on a feature beyond the point of diminishing returns. Maybe your product has already met the client specifications, but you add in more stuff thinking that that'll be useful to the client. But all you're doing is adding complexity to your code and having your team do work that may not really be useful. Another example of a software design anti pattern is the input clutch. This is when you, as a developer, have not added validation to detect invalid inputs in your application. Input clutch typically arises when you have not really thought through what kind of user input will be provided to your app. Invalid input can often result in app crashes. Another example of an anti pattern is interface bloat. This is when you make your interface so powerful, contain so many methods, do so many things that it's difficult to implement and use. Interface bloat occurs when you write code without following the interface segregation principle, which calls for smaller and more granular interfaces. Another example of an anti pattern is the race hazard or a race condition. This is where you've not taken into account the interference between multiple events. A race condition occurs in your system where your system's behavior is dependent on the sequence or timing of other uncontrollable events. If the timing or order of events change, your system might react in a way that you do not expect and which is not correct. In such situations, these race conditions manifest themselves as bugs. Race conditions prove extremely hard to track down and fix in the real world. Another example of the software design anti pattern is the abstraction inversion. This is where your component or system has the implementation that clients need, but you haven't exposed that important and required functionality via the interface for your system. Because you haven't exposed the functionality that clients need, it's quite possible that your clients will end up re implementing that functionality themselves, which is quite a waste. Another common term for anti patterns is code smell. Here are some anti patterns for object oriented programming. Now, in an object oriented programming hierarchy, if you require that all of your derived classes to call the superclass method without which the derived class does not work correctly, well, that is an anti pattern or bad programming practice. You should be able to write code in derived classes without having to call the superclass method. This anti-pattern is called the call super anti-pattern. The next anti-pattern that we'll discuss here is one that I'm afraid I have been guilty of, the circular dependency. This is where you have different modules of your code depend on one another in such a way that your module dependencies become very complicated and very hard to manage. So, updating any one module becomes close to impossible because you have no idea what other modules may depend on that module, what other modules may be affected. A circular dependency here is a specific condition where you may have module A, which depends on module B, B depends on C, C depends on D, and it's quite possible that the developer working on module D has no idea of other dependencies in the system and ends up depending on module A. Maintaining and updating such systems is basically a nightmare. Here is an example of another anti pattern, which I think has an interesting name, the God object. Now, the God object is what results when you don't follow the interface segregation principle. You concentrate so many features in a single module or a single component that it is all powerful. Developers here usually start off with good intentions. They want to put code which is related together in the same place, but they assume that the relationship is closer than it actually is. You end up adding more and more functionality to the same component till everything you do requires invoking that component. That component becomes clunky, hard to maintain, and in general, very, very difficult to work with. If you have the God object problem, the best thing is to refactor your code into smaller modules that are more cohesive and logically contained. Yet another example of an anti pattern commonly seen in practice is sequential coupling. Let's say you have a class or a component which exposes a number of methods. Now, in the documentation for this component, you might specify that method A absolutely has to be called before method B, but you don't enforce this in code. Now, users or clients will have no idea this logical ordering exists between methods of a component unless they actually check the documentation, and you can't assume that everyone will read the documentation before using your component. Clients will end up using your code in unexpected ways, leading to hard to track down bugs. We're in the midst of an interesting discussion on anti patterns, code smells, or common flaws that you might encounter in code that exists in the real world. Let's move on to discussing some specific programming anti patterns, and the first one is called action at a distance. Now, this is behavior that code exhibits when there are different components which make up your system, and there are two components which are far apart in their behavior and usage, but they still depend on each other in some unexpected manner. So there is unexpected interaction between the components that you've built. The way this manifests itself is that the behavior in one part of your program varies wildly based on difficult or impossible to identify operations in another part of the program. The way you avoid this anti pattern is avoid the use of global variable and make sure you alter data only in a controlled and local manner. And here is one anti pattern which I've seen very often in the real world: the boat anchor, retaining a part of a system that is no longer useful. Now, typically in organization, the code base is built up over years. Now, it might be that developers have moved on to a new feature or a new part or a new component in the code base, but the old component is still left around just in case we need it. Obviously, no one actively maintains this code, it soon becomes obsolete. Now, all of the members of the team might change, but when new members of the team come in, they have no idea what code is obsolete and what isn't, and they might end up spending a lot of precious time and resource trying to fix bugs in code that is no longer being used, that is no longer needed. That is the boat anchor. As a developer, you need to have a plan to deal with code that is obsolete. It needs to be phased out and deleted from the code base so it doesn't waste the time of developers who come in after you. Let's move on to the next anti pattern, that is busy waiting. Now, in the real world, there are certain operations that are long running, and maybe these operations depend on external input, such as user input or external events that need to occur. Now, if you have other processes in your system that are simply waiting on this external event and taking up CPU cycles, well, that is a tremendous waste of compute power, and that is busy waiting. The term busy waiting, busy looping, or spinning is also used when a process repeatedly checks to see whether a condition is true before moving on with its operation. A way to avoid busy waiting is to have asynchronous operations with callbacks, and your callbacks are executed when the asynchronous operation is complete. Your code does not have to wait for the completion of an operation, it will be notified when things are done. Another commonly encountered anti pattern is coding by exception. This is where, as you write code, you think of new cases that might be encountered by your system, and for every special case, you add in additional code. Think of a massive number of if else statements. That is an example of coding by exception. This anti pattern can quickly degrade software performance and maintainability. Now, the way to avoid this is to step back and see if there is a general root cause behind all of these exceptions that you're building into your program, and try and code something that fits multiple cases instead of treating each case in isolation. And here's an anti pattern which I'm sure all of you are familiar with: hard coding, embedding assumptions about the environment in the system. Now, hard coding comes in many forms. This anti pattern usually occurs when you go from your prototype to production code very quickly without much thought. When you're building your prototype, it's common to hard code in assumptions and not read in data from the environment. But when you move to production, you have to be careful about eliminating these. Now, if you're programming using an object oriented language such as Java, it's common to use inheritance to solve for many design cases. Now, that's where you might run into the lasagna code anti pattern. This is where your program contains so many layers of inheritance that changing one layer is impossible without changing all of the other layers. Lasagna code occurs when you know that inheritance is a good design strategy under certain conditions, but you try to apply it to too many different cases where it may not make sense. You end up introducing too many layers of inheritance, and that's an anti pattern and leads to poor software, which is hard to maintain. Now, all anti patterns have interesting names, but this one is one that I like particularly, the diaper pattern. This is where an error occurs somewhere within your software. You catch that error and then show a meaningless message to the user, and you don't pass information about this error to other parts of your system. Other terms that are used to describe this diaper pattern are error swallowing and error hiding. This is where errors which occur are not logged meaningfully or passed on to components which need to know of those errors, but instead you try to catch those errors, swallow it, not do anything about it, but try to get on with regular processing. Now, this is considered bad practice because when bugs do indeed occur in your software systems, swallowing or hiding errors can make these bugs harder to track down. When you're writing code, make sure you actively log errors or throw exceptions, don't hide errors. The next anti pattern we'll discuss is called lava flow. This is when you keep low quality code around because removing it is expensive or unpredictable. All of these anti patterns add to what is called tech debt, technological debt that you accumulate over many years as you write code and don't clean it up. The term lava flow often refers to code that has been written under suboptimal conditions. Maybe it's written when there was tight pressure on a deliverable. Maybe it was written during the prototype phase, but it wasn't updated and refactored and set up correctly for production. Now, this code comes to production somehow, and once it's there, it obviously has to be maintained. This can put a tremendous burden on developers for many years. You might be better off taking a one time hit and cleaning up this code and dealing with its unpredictabilities. Now, the next anti pattern that we're going to discuss, called magic numbers, is one of the oldest anti patterns out there. It dates back 40 or 50 years back to COBOL programming and Fortran programming. The use of unnamed magic numbers in code obscures the developer's intent in choosing that number. You have no idea why the original developer picked that number specifically. This increases the opportunities for subtle errors and makes it more difficult for the program to be adapted and extended in the future. If you're using numbers in your algorithm, your numbers should be assigned to constants which have clear names and are well documented. Another anti pattern found in programming is the shotgun surgery. This is where you add features with many implementations in a single change. Now, when you make changes to your databases, you do so using change lists, say using a source control repository such as Git or GitHub. Now, if you try to make too many changes as a part of one change list or one commit to your repository, these changes become harder to debug and harder to roll back. If there is a problem with one implementation, the commit, which may include many other features that work correctly, will have to be rolled back. The commits to your source control repository should be logical, cohesive, and deal with a single issue. The next anti pattern is one that I'm sure that you have heard of because this is one that is often committed by novice developers. Maybe you've been guilty of it, maybe you've seen others on your team who are guilty of this spaghetti code. This typically refers to code that is incomprehensible or has no clear logical structure. Code which does not use functions for logical units for reuse. Code which points to other parts of the code and randomly jumps around with no clear pattern. All of these are examples of spaghetti code. And here is a programming anti pattern for advanced developers who want to improve the structure and design of their code by using design patterns. Cargo cult programming. In general, applying and using design patterns is a good thing. But if you include design patterns in your code just because you have to or you think you should without understanding the why and without applying it in the right context, well, you're guilty of cargo cult programming. This style of computer programming is characterized by the ritual inclusion of code or program structures that serve no real purpose. Let's discuss a few more anti-patterns before we continue our discussion of design patterns. Here is one that I've definitely been guilty of: copy and paste programming. Now, this occurs when a novice programmer is coding and is often under pressure to deliver results. She knows that she is under pressure and she knows that a solution for this exists elsewhere in the system, though it may not be an exact match. Then she goes ahead and copies that solution and pastes it in without really understanding what it does, without putting that code into a reusable function or component. This kind of repetitive code blindly copied in becomes unmaintainable. What if there was a bug in the original code? The other developers may have fixed that bug, but you have no idea that the same bug exists in your system. Don't copy paste code, create reusable components so that all teams can make use of that functionality. The golden hammer is a programming anti pattern, and it's also a term for a cognitive bias. This is a cognitive bias that involves an over reliance on a familiar tool. This is where you assume that a favorite solution, either yours or your team leads, is universally applicable. For example, maybe modeling entities using inheritance has worked very well for you in the past and has solved many problems. But you might end up using inheritance when some other structure might be needed, such as composition or delegation. Here is an anti pattern that is very common in organizations: reinventing the square wheel. You know there is an existing solution out there, but it hasn't been developed within your org. Instead of adopting that solution and maybe tweaking it for your use case, you reinvent the wheel and end up using a worse custom solution just because it was developed within your team or within your org. It's called reinventing the square wheel because the wheel that you have created is worse than the circular wheel already implemented elsewhere. An anti pattern that is closely related to the golden hammer that we discussed earlier is the silver bullet. This is where you assume that a favorite solution can solve a more complex, larger problem. It's similar to the golden hammer. In the golden hammer, you think that a favorite solution is universally applicable. In a silver bullet, you take something that has worked in a small, narrow context but try and apply it to a larger context where it's bound to fail. When you write code in the real world, there are many libraries that you may depend on. Now, these libraries have versions, and as new features and functionality are added to those libraries, new versions will be released. Now, dependency hell is when you have too many versions of libraries that are almost impossible to manage. Dependency hell is closely related to DLL hell, where there is inadequate management of dynamic link libraries, DLLs, specifically on the Microsoft Windows operating system. It's also related to jar hell, where you overutilize multiple jar files. These are Java archives, and this leads to versioning and location problems. The next anti pattern is one that I believe is more common with experienced developers rather than novice developers: premature optimization. You code for perceived efficiency and good design before the problem is solved. Now, it's good to have efficient, performant, and optimized code. It's good to refactor your code into reusable components. But if you do it too soon, all you'll end up doing is refactoring and cleaning up code. You won't actually accomplish what you set out to do. There is a delicate balance that you need to maintain here. You need to code to make sure that your problem is solved, your end goal is achieved. Once you have that, you should refactor and set up all of the optimizations in your system. Let's conclude our discussion on anti patterns by discussing a few that are specific to JavaScript. When you define a large number of functions and variables in the global namespace, well, that is an anti pattern. Now, anything you define outside of a module in JavaScript is in the global namespace, and it's very common in JavaScript to have developers pollute the global namespace, leading to conflicts and name resolution issues. In a very large code base, global variables, global functions are almost impossible to manage. And this is what leads to interaction between components which may not be related to one another. Make sure that all of your variables and functions are within a module, not in the global namespace. The next anti-pattern that is specific to JavaScript is passing strings rather than functions to set timeout or set interval and depending on them to be passed through the eval function. Browsers support the set timeout function, allowing you to execute code after a certain timeout. They also support the set interval function, allowing you to execute code repeatedly after specified intervals of time. Now, these functions can accept a function object. They can also accept strings, which are then evaluated using the eval function available in your browser. Passing in strings expecting that they'll be eval can cause security issues and all kinds of other problems. Pass in function objects instead. In JavaScript, all objects inherit from the base object class. And every object, the base object as well as objects that you create, have a prototype property, which is what allows for prototypal inheritance. Now, you shouldn't be modifying the object.prototype directly. You should define your own objects with their own methods and their own properties. Modifying the object prototype may cause unexpected behavior in other parts of your code that extend the base object. Another anti-pattern commonly seen in JavaScript is using document.write rather than native DOM alternatives such as document.createElements to create HTML to be embedded within your page. Using document.write has particularly bad consequences. Especially if it's executed after the page has been loaded, it can actually overwrite the entire page that we are on. Whereas document.createElement creates specific elements which then become part of the DOM hierarchy. Now that we understand the principles of good design that should underlie any code that we write, and we also understand anti-patterns and code smells that we need to avoid, let's move on to discussing design patterns. We know that design patterns are reusable solutions to common problems, and design patterns can be divided into three broad categories or classes. Let's look at what these are. The first category or type of design patterns that we'll discuss are creational patterns. Now, creational design patterns have to do with how objects are constructed and instantiated in your code. Creational design patterns focus on handling object creation mechanisms where objects are created in a manner suitable for the situation or the context in which we are working. Now, object creation can be arbitrarily complex, and these patterns aim to solve or abstract away this complexity by controlling the creation process in a well defined manner. The second category into which design patterns can be classified is structural design patterns. Now, structural design patterns focus on how components within your system interact. Structural design patterns aim to make your design more intuitive and simple by identifying a simple way to realize the relationships amongst entities or components in your system. This might involve abstracting away parts of the system so that when one part changes, other parts need not have to change at the same time, decoupling components so that they can be versioned separately, etc. And finally, the third common category into which design patterns fall is behavioral design patterns. Now, behavioral design patterns are also focused on components, but they're focused on how components communicate with one another. The objective of behavioral design patterns is to identify common communication patterns amongst objects and realize the right structure to set up this communication. Now, there are other ways to classify and categorize design patterns, but these are the most common and the most universally applicable, and this is what we'll work with. Let's discuss each of these in a little more detail. We first discussed creational design patterns, which are patterns that focus on instantiation of objects and is relationships. These patterns will try and answer questions such as how do you create objects that are very similar to one another? How do you abstract away the complexities of creation from the client code? After creational patterns, we have structural patterns which focus on the structure of your system, how components within your system interact with one another. Structural design patterns are patterns that focus on composition and has relationships that exist between your entities. And finally, we have behavioral design patterns that focus on how objects communicate with one another as well as with the external world. I'll now discuss each of these classes or categories of design patterns in a little more detail, starting with creational patterns. This is where we seek to control object creation, so the complexity of creation is abstracted away from the users or clients of the system. You might want objects to be created with a certain number of default properties. You might want objects to be built up in a step by step manner. You might want just a few instances of the object to exist within your program. All of this is possible using creational patterns. The name of this category of design patterns, creational patterns, make it very obvious that these patterns relate to how objects are constructed or built up within your system. The main purpose of creational patterns is to seek to decouple the construction of an object from its use. How an object is set up, how it's created, is completely different from how that object might be used. So, clients which use a particular object need not know of the complexities of construction. That's the idea. So, what we are looking to do with creational patterns is hide the implementation of an object and only reveal its interface, that is, the behavior of an object. You, as a developer, want to provide an API or an interface or an object for clients to use. How that object is constructed? Well, that's your business. Clients need not know of the complexity. Your aim should be to make it as easy as possible for them to construct objects for use. The use of creational patterns also allow for other advantages and optimizations. For example, lazy instantiation. This is where you defer the creation of an object till runtime, that is when the object is actually used. Let's say you have a complex object that takes up a lot of resources, maybe in the form of memory, maybe in the form of external connections to databases. Ideally, you would not want to create this object unless it was absolutely needed, unless there is some client code that requests this object. You can defer the creation of this object till someone has asked for it. That is lazy instantiation, and that is possible using creational design patterns. When you're writing code, it's quite possible that you have families of objects that must be created together. Let's say you're setting up a database connection object and you have an object to control or secure access to that database. Let's say both of these objects have to be created together and you want to enforce this in your code. It's possible to do this using creational patterns. You can control the creation of all objects in a family of objects that must be used together. Creational patterns can also be used to constrain the number of instances that you can create for a particular object. Let's say you have a database and you want to make sure that you have just 4 or 5 connections to that database across your entire application, because additional connections slow your database down. You can enforce this creation of just a finite number of instances. Here, the instances are database connections using creational patterns. From creational patterns, let's move on to discussing structural patterns, where the primary focus is on how classes and components can be composed to form more complex structures. Any complex system has many moving parts, and all of these moving parts are components, classes, or objects within your software system. Now, the idea behind structural patterns is to identify the relationships that exist between these entities or components in your system, and then find a way to express these relationships using a robust design. Now, with structural patterns, you'll see that the focus is often on class inheritance to model different kinds of behavior, or object composition to have simpler components come together to build up more complex components. Structural patterns also allow you to work with legacy components in your system without burdening your clients. They also give you the ability to add responsibility to your components dynamically at runtime. And finally, we have behavioral patterns that focus on the responsibility of individual components and how they communicate and interact with one another. Now, all of the moving parts in your system, your components, need to be able to interact and communicate with one another. Entities should be able to easily communicate with one another. This communication should be clear, well defined, and should have a clear flow from one component to another. However, these entities which are able to communicate easily should be loosely coupled. They should not be tightly coupled. Changing one component or an entity should not result in us having to make changes to the other component. In order to ensure that components can communicate but still be loosely coupled, we need to make sure that these interactions avoid dependencies. Components should not depend on other components in order to be able to communicate with them. Both structural and behavioral design patterns deal with components, how systems are set up, and how components interact. So, what's the difference between them? With structural design patterns, we are focused more on how components or classes within a logical unit interact with each other. The entities that we deal with in a structural design pattern are all components within the same system. Structural patterns tend to deal with the interaction of components that are internal to a system. On the other hand, behavioral patterns focus on communication and relationships and govern how a logical unit as a whole interacts with the outside world. So, how a system talks to other systems which live outside of it. Before we get down to seeing how the different design patterns are implemented in JavaScript, let's get set up. Here are a few things that you need to install in order to run the code for all of the demos here on in. Now, in order to run the demos, we are going to install a very simple, lightweight HTTP server onto our local machine. And in order to install that server, we need the npm package manager, which we'll get from nodejs.org/en/download. If you worked with JavaScript, it's quite likely that you encountered Node.js before. Node.js is an open source cross platform JavaScript runtime that can run JavaScript code outside of a browser. So it has the ability to compile JavaScript outside of a browser and run it, and it's often used to run JS on the server side. Now, we won't really be using Node.js to run JavaScript code. In order to implement the different design patterns that we'll be studying in this path, we'll use pure JavaScript wherever possible. We'll sometimes use the jQuery framework. You don't need to know jQuery upfront. I'll explain whatever is needed to know. Or we'll use the React component driven framework. Once again, you don't need to know these libraries upfront in order to understand the demos of this course, but a little bit of knowledge about all of these common JavaScript frameworks would definitely help. Now we are going to install Node.js, and you can see that it's available for all of these different platforms in order to use the npm package manager. We'll talk about why we need npm in just a bit. Go ahead and get installed for the kind of machine that you're working with. I'm currently on a Mac OS machine. That's why I've selected the Mac OS installer to be downloaded onto my local machine. If you're on a Windows machine, go ahead and set up the Windows installer. The setup for Windows is very similar to that of the Mac, so you can simply follow along. You can see that the Node package is now available on my local machine. I'm going to click on that little arrow there in order to find the node package on my local machine. When I click on show in finder, this will bring up a finder window on my local machine, and you can see that the node package has been installed here. I can now double click on this package in order to start the installation process for Node.js and for the npm package manager. The installation wizard that comes up here very clearly indicates that Node.js version 12.14 will be installed, as well as the npm package manager version 6.13.4. And it will also specify the directory where this will be installed. I'm going to go ahead and click the continue button because I want to continue with the installation process. When the software license agreement comes up, make sure you read it if you want to, but I'd just go ahead and accept it. This is common software, open source software, commonly in use by all JavaScript developers. Hit continue and agree with the software license and move on. This will bring up a wizard screen asking whether you want Node.js to be installed on your local machine. Click on the install button, hit yes, and move on. Make sure you type in your username and password because you'll need admin privileges to perform this installation on a Mac and even on Windows. And that's it. This completes the installation process. Once install is complete, you can click on the close button to get out of this install wizard. You can choose to keep the installation package or move it to trash. I've chosen to keep it for now. Once you're done with the install process for Node.js and npm, I'm now going to switch over to the terminal window on my Mac machine. I'm going to run the command which node, which will tell me where exactly this node.js has been installed. You can see that it is in user local bin node. Well, we are not really going to be using Node.js directly. What we are really interested in is the npm package manager. So I'll run the command which npm, and this tells me that the npm package manager, called the node package manager, has been installed in user local bin npm. The next step is to check whether this user local bin directory is referenced as a part of my path environment variable. So I'm going to run the command echo $path to see whether this directory user local bin is a part of this environment variable. And if it is, I'm all set. I can run commands and packages that have been installed in this directory. You can see that user local bin is indeed present as a part of my path variable. If it is not, you can always set it using the set command. If you find that folder where you have Node.js and npm installed is not part of your path environment variable, you can use the set command as you see it here on screen. Set $path is equal to $path colon / user local bin. Once your path environment variable has been set up correctly, you can go ahead and run node and npm commands. Let's take a look at the current version of node that we have installed by running node-v. It's currently 12.14.0. This is the latest version at the time of this recording. In exactly the same manner, we can run npm-v to see the version of npm that we're using for all of the demos of this course. The npm version that we have is 6.13.4. Once again, the latest version at the time of this recording. We are all set with the versions now. We are ready to get started. I'm now going to use the npm package manager in order to install a simple lightweight HTTP server to run my JavaScript code. Before that, let me formally define what npm is all about. This is a package manager for JavaScript. It contains both public as well as private JS packages which you can install on your local machine in a very straightforward manner. Once you have npm installed, using the npm package manager is simple. Simply run the npm install command. The -g option will install this HTTP server package that I'm downloading onto my local machine as a global package that is available in all contexts. So now that we know what npm install works, let's quickly talk about the sudo here. In order to install this package, I need administrative privileges, and I'm going to run this command using sudo so that I have admin privileges to install and download this package onto my local machine. The sudo in your command here will ask you for your admin password in order to execute this command. Make sure you type in the right password here, and npm will start the download and install process for HTTP server. The next question that you might rightly ask yourself here is, what exactly is this HTTP server that we are installing? HTTP server is a simple zero configuration command line HTTP server that is available as an npm package. It's available completely free. Anybody can download and install, and you can run a simple server on your local machine, which is where we'll host and run our JavaScript code instead of accessing our HTML and JavaScript directly using file URLs. Having this little HTTP server setup makes things very simple overall, because you'll have all of your code running on a certain port and you can navigate your server directory easily. Running this command here, http server followed by a dot, will start your HTTP server from the current working directory. So make sure that you're in the working directory where you plan to write your code. Executing this command will bring up your HTTP server, and you can see that it's available at port 8080 by default. If for some reason port 8080 is occupied because of some other server that you have running, this server will start up on port 8081, then 8082, and so on. You can access this server by simply copying over this URL here, 127.0.0.1 8080, and paste it onto a new browser window. And once you've pasted this in, this will take you to a directory listing of the current working directory. This is the directory where you started up your HTTP server. This is the directory where you will be writing your code. And if you want to kill this server, well, simply switch over to the terminal window and hit Control C. That will stop the HTTP server. Now that you know how to start and stop this HTTP server, we're ready to get coding. If you're working on a Windows machine, this demo will get you up and running with the Node.js runtime environment and the NPM package manager. Node.js is a runtime environment that allows you to execute JavaScript written in .js files without a browser. The Node.js runtime environment comes with a popular package manager known as NPM. This is a package manager for JavaScript. It contains public as well as private JS packages. Once you install Node.js and NPM onto your local machine, you can then use the NPM package manager to get any additional JavaScript packages that you're interested in. And we'll be using NPM to get an HTTP server package, which we'll use to serve and host all of the code in this design patterns course. Now, Node.js is available for download if you head over to this URL nodejs.org/en/download. Once you're in this downloads page, you can see that the latest version of Node.js available at the time of this recording is 12.13.1, and this includes NPM 6.12.1. You can see that Node.js can be installed for Windows as well as Mac machines. If you're working on Windows, the Windows option is what we'll choose. Clicking on the Windows installer here within this window will download the MSI package that will walk you through the install wizard to set up Node.js and the npm package manager on your local machine. You'll first need to download Node onto your local machine. Click on Save and save this package to the Downloads folder. You might have to wait for a few seconds till the MSI has been downloaded and is available on your local machine. Once the installer has been downloaded, you can click on this little arrow icon here and find this MSI within your Explorer window. Select the option to display this within your folder, and you will be taken to the folder where this MSI has been installed. This is in my Downloads folder. I'm going to maximize this folder window here so that we have more room to work with. And once that is done, you can double click on this Windows installer package, and this will bring up the Node install wizard. You can see that this wizard installs Node.js on your computer. Click on the next button here in order to walk through the installation steps. Here is the license agreement. I suggest you just go ahead and accept it if you want to be able to work with Node and the NPM package manager. Select this checkbox here that accepts the license agreement. Once you've selected this checkbox, you can click on the next button here and move on to the next page. You can select the folder you want Node.js to be installed in. Here it is in C program files Node.js. This is acceptable to me. I'm going to click on next and move on. On the next page, you'll see displayed a list of all of the actions that will be performed. The Node.js runtime will be installed, as well as the NPM package manager. Online documentation shortcuts will also be installed, and Node.js as well as NPM will be added to your path environment variable. Well, this is exactly what we want. I'm ready to hit next and move on to the next page in my install wizard. Hit next and move on to the next page of the install wizard, and this brings us to the last page. Hit installed to get the installation process started. You might have to wait for a couple of minutes till all of the packages are downloaded and installed onto your local machine. Hopefully, you'll see this happy message very soon which says Node.js has been successfully installed. Click on Finish and you're ready to get started. If you feel that your environment variables haven't been configured correctly, we can confirm this. I'm going to select this PC node, right click, and choose the Properties option. That will bring up a dialog allowing me to access my environment variables. Head over to Advanced System Settings on your Windows machine, and you'll find a little button there saying Environment Variables. That's what you need to select in order to view and configure your environment variables. I've logged in as the admin user on this machine. Here are the user variables for the administrator. I'm going to scroll down till I find the path environment variable. That's the environment variable that I need to check and configure as needed. I'm going to hit the edit button. That will bring up a dialog allowing me to edit this variable. Thanks to our install wizard, the C program files and Node.js path is already present as a part of my path environment variable. If it isn't, all you need to do is click on the new button here and type in the directory where you have Node.js installed. This will now become a part of your path environment variable, and when you work within your DOS shell window, you'll be able to access Node as well as npm. Click on OK. Now that you've correctly configured the path for your current user, you can go ahead and hit the OK button on this dialog as well. You're done with configuring an environment, you can now switch over to a DOS shell window in order to continue working with Node. Here I am with my DOS shell prompt opened up on my Windows machine. I'm currently within the directory C users admin. Admin is my current user. I'm going to run the node-v command to see the version of Node that has been installed, and you can see that it is the latest version at the time of this recording, version 12.13.1. I'll run the npm-v command in order to see whether the npm package manager is available, and this shows me that the npm version 6.12.1 is installed and available here on my Windows machine. I'm going to use the npm install command in order to set up a simple HTTP server. The HTTP-server package is a simple zero configuration command line HTTP server available in npm. This server is extremely easy to install and set up, and it's also robust enough to be used in production. We just need it for our development environment though, so that we are no longer accessing our HTML files using the file system. Once HTTP server has been installed on your local machine, all you need to do to run this HTTP server is to run the command http server dot. The dot will basically specify that the current working directory is the base directory for your HTTP server. This will kickstart the HTTP server running, and it will be available by default on port 8080 of your machine. If your port 8080 is taken up by some other process that is running on your local machine, the HTTP server will pick 8081, 8082, and so on. It will search for the first available port starting at 8080. Let's head over to this URL 127.0.0.1 colon 8080, and this will bring up a directory listing showing the contents of your current working directory. This HTTP server is currently running within our DOS shell. If you want to stop the server, all you have to do is hit Control C and the server will be stopped. In this course, we introduced various principles of sound software design, as well as common anti-patterns. These included the single responsibility principle, the open-closed principle, Liskov's substitution principle, the interface segregation principle, and the dependency inversion principle. We saw how these principles lay the foundation for the various types of design patterns: creational, structural, and behavioral, which will be explored in depth in the courses ahead. In addition, we also comprehensively discussed several anti patterns, which are pitfalls to be avoided by software engineers and architects. We covered both general and JavaScript specific anti patterns. We have also installed Node.js and NPM on our local machines, setting up nicely to implement various patterns in the courses coming up next. You are now set up to explore creational design patterns in detail, such as the constructor, factory, and abstract factory design patterns.